Hi everybody, this is your first lesson for Chapter 5b. Now, the main topic for Chapter 5b is called logarithms. That's going to be our parent function for Chapter 5b, the logarithmic equation. Now, you will not understand what the logarithmic equation is until we've done the inverses lesson. So let's do the inverses lesson. First question, inverses, what are they? I looked up Google definition, and I have a definition for inverse. According to the internet, the inverse, the opposite or contrary in position, direction, order, or effect. A noun, something that is the opposite or reverse of something else. Those are actually some pretty good definitions. Those are pretty good definitions, but mathematically, how inverses apply with us. If you've done inverses before, you probably did something like you switched the x and the y. And that's really the best definition I have. Or if we took a function xy and we apply the inverse, all of the x coordinates become the y coordinate. And guess what all the y coordinates become? The x coordinates. And that is exactly what the inverse is. That's kind of confusing. So let's take a look at it two different ways. First, let's just look at it purely graphically. And this is going to make most sense on graph paper. So let's say I had a graph. Sorry about that, my hat just hit the screen. And had a curve like this, and it had the coordinate 0, 3, the coordinate, let's go with -2, 2, and the coordinate -4, 0. And let's say that it's connected with this curvy thing. If this is, and let's say that these points are all called f of x. Well, the inverse, by definition, the inverse is simply when you switch the x and the y coordinates. So the coordinate 0, 3 becomes 3, 0. The coordinate -2, 2 becomes 2, -2. The coordinate is -4, 0 becomes 0, -4. And if we connect the dots, we end up with something like that. Interesting. Let's try another one. Let's do something like square root x. If I think about those key points of square root x, I had a point at 0, 0, a key point at 1, 1, and a key point at 4, 2. So it would look something like that. Well, the inverse of that, the inverse of 0, 0 would still be 0, 0. The inverse of 1, 1, well, if you switch 1, 1, I guess that would still be 1, 1. But the point 4, 2, that becomes the point 2, 4. And then if we connected those dots, we'd get something like that. Now, you noticing some kind of pattern? Hopefully noticing a pattern. Let's do one more example. Example 3. On this one, I'm going to draw kind of an x squared looking graph. I'm going to put the vertex here at -3, 0. And if I think about parent points, over 2, up 4, over 2, 1, 2, 3, 4, I'd have a graph like this. So what would a parabola look like? Well, this coordinate is -3, 0. So you switch the x and the y, you get 0, -3. The point -2, 1 would become 1, -2. The point -4, 1 would become 1, -4. The point -1, 4 becomes 4,
negative 1. And then last but not least, the point negative 5, 4 would become 4, negative 5. And you connect those dots. Interesting. Our regular function was more of an x squared graph pointing up and down, or pointing up, whereas then our inverse would be pointing to the right. We're going to talk more about an example like this in the future. But are you noticing that we got kind of like a nice little graph thing that if we drew in the line y equals x, so I had the point 0, 0, 1, 1, 2, 2, 3, 3, opposite negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. You notice something interesting? What if I draw in this y equals x on this graph? Noticing anything interesting? What about this last one? If I drew in y equals x? Noticing anything interesting? Well, hopefully what you're noticing is that these two graphs are a reflection of each other over the line y equals x. And I can prove that by folding along the line. Sorry, I've run out of camera. So I'm folding along my inverse line. And then if I hold my graph up to the light, the two graphs are completely overlap with each other. So it's a reflection over the line y equals x. So graphically, that would be the best description. These are some great examples as to how you graph the inverses of graphs. But graphically, it is a reflection over y equals x is one way of thinking about it. Or if you're thinking about it using the coordinate technique, it goes from x, y, all of the xy coordinates are becoming yx. And that's the graphic explanation of inverses. The last thing I want to do is show the algebraic explanation of inverses. Algebraically. Number one, let's say that I had f of x equals 3x plus 7 over 2. All right, step one, change your f of x to a y because it's kind of confusing when to think about this using f of x and x. Sometimes it's easier to think about it using x's and y's. Second, by definition, switch the x and the y. So the y becomes an x. The x becomes a y. And now, last step, we do what we did for the weekend's homework. We solve for y. So I multiply both sides by 2. I get 2x equals 3y plus 7. Subtract 7 from both sides. So 3y equals 2x minus 7. Divide everything in the equation by 3. So y ends up equaling 2x minus 7, all divide by 3. 7 and 3 do not divide evenly. 2 and 3 don't divide evenly. So I'm leaving it just like that. And now to finish it off, it started off with f of x, so we need to answer as f inverse of x. And f inverse of x is equal to this stuff, 2x minus 7 over 3. Don't try to look for its shortcut. Don't think plus became minus and the 2 and the 3 got switched. That only works for example number 1. It's not a good thing to think about for the rest of my examples. Number 2. Suppose m of x equals negative 4 over x minus 3. All right, step 1, just like the last problem, change m of x equal to y. I'm doing a lesson on inverses. Yeah. So we switched the x, we've changed the m of x to a y. Now we'll perform the inverse by switching the x and the y. So y becomes x. x becomes y. And now that we've performed the inverse, we've got to solve for y. This one's a little bit more interesting. Let's see. I got this y on the denominator, and that's really the problem. So I'm going to start off by multiplying both sides by y minus 3 here. So I get y minus 3 times x equals negative 4. Couple different options here. I'm going to break off into two paths. I think the easiest way to go would be to divide both sides by x. So I get y minus 3 equals negative 4 over x. And then I could add 3 to both sides, and I end up getting y equals negative 4 over x plus 3. But some people see those parentheses and they're like, oh, I want to distribute. And you can distribute. You would get x times y minus 3x equals negative 4. Then you could add the 3x to both sides. So now I have x times y equals negative 4 minus 3x. And then I could divide both sides by x. And I end up getting y equals negative 4 over x. And when I divide 3x and the x, those would cancel out, and I'd get a minus 3. It sure feels like I've made a mistake somewhere. Oh, I did. On this step, from here to here, I should have added 3x to both sides. So it would be plus 3x, which means here it would be plus 3. Elliot saves the day. Between these two techniques, whichever technique is easiest on your brain is the technique you should use. I prefer this one because it's less steps, but if you prefer that one because you like distributing, you should do it. One more example for you today. Example number 3. Suppose g of x equals 5th root of x plus 6. I'm sorry, before I go to example 3, I got to go back to example 2. I forgot to finish the problem. If this is called m of x, the inverse is m inverse of x. So negative 4 over x plus 3. Got to make sure you answer the question at the end of the day, right? All right. Example 3. I have this. Change g of x to y. So 5th root of x plus 6. Subtract 6 from both sides. So y minus 6 equals the 5th root of x. 5th root of x, as you remember from our chapter test that we took on Thursday, 5th root of x is x to the 1/5, and you can get rid of that by raising both sides to the 5th power. Excuse me. And if I were to raise this to the 5th power, the 5th root and the 5th power cancel out, leaving x by itself. On this side, I'd have y minus x to the 5th power. That's too big of a number to multiply out. And students, my friends, that is inverses, both what they are and some examples. So anyway, have yourselves a beautiful rest of the weekend, and I will talk to you on Monday. Oh, I want a Big Elliot. Big Elliot. Have a great day. Bye-bye.